Okay, this week we're going to continue working on factoring. Um, we have looked at how to use the GCF to factor. We also looked at grouping. And then lastly, we worked with trinomials, which can be factored by splitting the middle term. Now, next thing is special forms. There are certain patterns that can be captured as a formula. And we're going to look at some of these special patterns or forms this week. Some of them were introduced in the video of the previous weeks as well. For example, difference of squares. The observation is if you take a plus b and multiply by a minus b, you get, and when you file out, you get a times a. You get an a times negative b. Okay, you get an a times a times negative b, and a b times a. Subtract b times b. The a times b and the negative a times b cancel, so you end up with a squared. A squared minus b squared, which is called a difference of squares. So this gives you an important way to factor something, right? Because you notice that if you have difference of two squares, or in the reverse direction, you can say a square minus b square factors as a plus b and a minus b. Here's the bonus solution from last week. Show the above relation using area. Now a squared here, it can be considered as a square with a side a, right? So the area is a squared, and b squared is the smaller area here. Now a squared minus b squared is the sum of these three areas labeled 1, 2, and 3, where that's 1, the horizontal 1, 2, and 3. 1 has sides. If this entire thing is a and the small thing is b, then what you're left with is a minus b. Similarly, a minus b here, and then you have b times a. Now all three rectangles have at least one side a minus b. You can stack them up. And when I stack them up, what's this bigger length? That's a minus b plus b plus b, which is a plus b. And the bottom is a minus b. So the area of this rectangle is a minus b times a plus b. So essentially giving you the same result that we have seen, that a squared minus b squared is a minus b times a plus b. Okay, let's look at an example of this. Factor completely. When something says factor completely, this means factor into as much as possible, right? And it'll be clear what I mean by as much as possible. 81x to the 4 minus 16. Few observations here is that 3 to the power 4 is 81, and 9 squared is 81, 2 to the power 4 is 16, and 4 squared is 16, right? This, by the way, is a unique situation where x to the y equals y to the x, right? Given x does not equal y. Of course, 1 to the 1 equals 1 to the 1. If x equals y, this is always true. But that's the only case when x is not equal to y, and this is true. Only when you pick the values 2 and 4. Okay, anyway, so I can write 81x to the 4 as 9x squared whole squared minus 4 squared. Now this falls into my pattern of a squared minus b squared, which would become then a minus b and a plus b. So because it says factor completely, you cannot stop here. Yeah, because what you observe is, well, there is still a 9x squared, which can be written as 3x whole squared, which is another a squared minus b squared situation. And it gives me 3x minus 2, 3x plus 2, and a 9x squared plus 4. So that's the, we would call this the complete factoring. Okay, so you may have to apply it twice. That's can happen if you're factoring completely. Then there's a perfect square trinomial. The pattern is that if you have a plus minus b squared, it becomes a plus minus 2ab plus b squared. So notice the a squared plus b squared, these remain the same. The only sign that changes is for the AB term, and it's because of the differences in sign between A and B in the parentheses. In reverse, always, it gives a way to factor, because remember, foiling is just the inverse process of factoring. For example, here, I have x squared plus 14x plus 49. You can follow your previous method of finding two numbers whose sum is 14 and whose product is 49. And when you do that, you're going to end up with the same thing. Was 1 plus 49 is 50. So no, 7 times 7 is 14. So okay, that works. Or you could observe that 49 is 7 squared and that 2 times 7 is 14. So it fits the pattern of x squared plus, I can rewrite 14 as 2 times x times 7 plus 7 squared, and that gives me x plus 7 whole squared directly. Now I could also use this for trinomials with two variable. So I notice here I have 2x squared, and then 12xy can be written as 2 times 2x times 3y, and 3y squared can be written as 3y whole squared to get 2x plus 3y whole squared. Now, let's look at an example where there is a negative. Because of this negative gives rise to a negative here. A little more complicated example, x squared minus 8x plus 16 minus y squared. Now here, I'm going to look at just the first three terms, and I notice that the first three terms can be written as x squared minus x squared minus 2 times 4 times x plus 4 squared, which is nothing but x minus 4 whole squared. So that this entire stuff becomes x minus 4 whole squared minus y squared, which is now a difference of squares, which becomes x minus 4 minus y and x minus 4 plus y. So that's another trick. You may have four terms and one of them may be a perfect square. Next example, we use the same trick, but this time we observe that all the b terms are towards the end. So we isolate them by inserting a negative in front and getting a b squared minus 10b plus 25, which becomes b minus 5 squared. And at this point, we use over here, we are using the difference of square formula. And we end up with a minus b plus 5 and a plus b minus 5. The next video will talk about sums and differences of cubes.